Hey guys, Sebastian here with another Cardano video. This time we're going over Marlowe, which is a system for creating financial contracts on a blockchain. And so the way this video is going to work is first I'm going to tackle the problem from a kind of high level overview where you don't need any programming language knowledge to kind of figure out what's going on. And then later on I'll go more into the code and show you guys kind of how that works. So first off, what is Marlowe, how does it work, and what are kind of the decisions that went into it? Well, first of all, in this paper, Marlowe, although in the future is planned to run on Cardano, in this paper is laid out as just a blockchain independent way of creating financial smart contracts. And in fact, the way it's specified in this paper is that it runs off of Haskell. So you'll have kind of a domain-specific language that runs inside Haskell. And the idea being that this is easy to test. You get all the tooling, the support, and all this kind of great stuff you get from the ecosystem that's been around for a long time. And then if you would want to integrate this into your blockchain, then all you'd have to do is kind of replace the primitives, I guess, if you will, to swap out Haskell with whatever platform you'd want. And so in the future, when this is available, you would have this run on Cardano, probably compiling down to Plutus, which is one of the languages that IOSK is currently researching and also developing. And so kind of the idea is once all this would be in place, there would be a Marlowe testnet where this would all get spun up, and then if everything goes well, this would be deployed on mainnet. And so another note is that smart contracts, for example in Ethereum, run on something called the accounting-based model, right? And that's different from what Bitcoin uses, which is called UTXO. So it's a different accounting model. And the reason there's this difference is because smart contracts tend to be more efficient and easier to create on an accounting-based model blockchain. And so if you don't know what that is, that's fine. Maybe you can pause the video and go look it up or go check it out later. But the thing with Marlowe is that it's specified in such a way that they don't really mind if it's accounting or UTXO based. It's kind of one layer up in abstraction, and they later say, okay, we could use either of them, and it's kind of still a debate internally whether or not you will be able to run this only on the Cardano computation layer, which is one side chain, or maybe you could also run it on both. Right? You could either run a computation layer, or it may make sense to also allow this on the settlement layer. And the reason I say this may make sense to run the settlement layer is because Marlowe is a very restricted environment, right? The amount of stuff that you can do on this through this domain-specific language is fairly restricted to guarantee a certain set of properties that we'll see later on to make sure that the gas costs can be predicted efficiently. They're always finite and all this kind of stuff. To make sure you don't get these kind of like runaway programs that may cause problems in the UTXO space. Alright, so now that I've given you guys the big picture overview, let's go slightly deeper into the details that's laid on this paper. So this is kind of what a script would look like that runs on Marlowe. You don't have to worry about this too much. I'll go into detail later on in the presentation about how this corresponds to Haskell code and all this kind of stuff. But this is kind of what it looks like visually, and I'll show you guys the editor for this later on, which is more like a CEO friendly. Because that's one of the goals of this programming language, basically, is to be like, you don't need to know how to program, as long as you can read English and kind of figure out basic logic. Should not be that hard to figure out. And so it should also be easy to verify there are no bugs, because you can kind of give it a glance, see what it looks like, and make sure, oh yeah, that makes sense. So what does it kind of look like? Well, we have the smart contracts running, and the way Marlowe is set up is that in the Haskell environment, it simulates blocks. Okay, so I'll show you guys later. There's going to be like a block counter and there's going to be discrete actions and discrete inputs. So that's what it's kind of showing in this picture up here, is that users can come into the system and then make certain sets of actions that'll update your Marlowe contract. And then from the outside, you can also get stuff that comes in. For example, Marlowe would like to eventually have good support for oracles in this kind of system that allows data come from the outside. So you could have a financial contract that says, for example, like if the price of oil, blah, 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 do this kind of thing. And so that's kind of where the outside comes from. And that's kind of the small picture. So the way this works is that there's going to be steps in the system, and these steps are laid out such that the step has the set of inputs that are the user inputs, right? And then you take the current state of the smart contract, the contract code itself, and then OS kind of represents like the environment. So it's not, for example, like a current block, maybe like a random number that comes from the underlying blockchain, this kind of stuff. And then with these 4 inputs, you will update the state, and you'll get your new state with the updated contract. And I'll show you guys in a bit later how this contract actually changes. So like here you can see you take the contract input and you have another contract as output, and I'll show you guys how that actually dynamically updates the contract as the execution progresses. And then lastly, there's going to be a set of actions that are enabled at the end. And I'll show you guys in the UI how these actions kind of allow the users to have a restricted set of things they can actually do. So I think that's all I really want to show you guys in this paper. And the reason I don't go more into it, despite the fact it is 20 pages long, is because afterwards it really just goes into the code, explaining what the code does. And so before I go into that, I want to show you guys what it looks like briefly. And then when it comes to the code, I feel like it makes more sense to kind of just actually show you guys what the code looks like. So we'll open that up later on. But alright, so let's jump right into Marlowe. So this is a website that's hosted by OHK. The link to this website will be in the description if you want to come try it out yourself. And this web page essentially just shows you a Marlowe smart contract rendered inside your browser. And inside your browser, you can kind of play around with it, create your own smart contracts, and then simulate the execution. So let's kind of see what it looks like. On the left-hand side, you can see we have the actual smart contract written as these boxes that are kind of clunky. So you see we have our smart contract designed by contract, and then first we say, okay, well, if you commit some cash, just deposit some cash into a contract. You know, for example, here's like a deposit 100 ADA. Then you can have conditions based on like timeouts and cash being committed by a different person. All right, so first I put in cash, and then another person puts in cash, and then now we both have some money in the system. And then so this is kind of how you would build up a contract. And as you can see, like these are actually like a kind of puzzle piece like boxes. And so let me try and put this back together. Yeah, so you can see I can snap stuff in. I can take this out. I can open up a menu on the left to like take more boxes and add it in. And so you don't need to like really know how to program to be able to play around with this. And so this is kind of how you would design your smart contract. At the top right over here, you have the actual code that these boxes represent. So you can see we have our commit cache box at the top left, and that's what our commit cache box is up here. So you can see kind of the code that this would compile down to. And if you want to see even further, actually, like I mentioned, this code actually in the example, or I should say in the current version of Marlowe described in the paper, it's actually part of Haskell. And so the way this all works is, if you want to know kind of how it works from a technical point of view, is that this uses this, 2 systems, one called Fay, which from what I understand is like a reduced version of Haskell, so kind of takes away some of the features. and then uses GHC.js to compile JavaScript, Haskell down to JavaScript to then render in your browser. So whenever you try something out on this website, you're trying it out on your local JavaScript running inside your browser. But you can see now that I've pulled up this menu, for the people who are more interested in the tech side, you can see we set up the Haskell code kind of up here, and then we create the actual contract. And so if you wanted to play around with this, you could, have your own Haskell-like definitions and just like plug stuff in. And then you'll be able to execute at the bottom left to update the actual code that is used based on this Haskell code. And so actually what will happen if you run this is that it will run the execution and then replace all the variables with the constants to then generate this contract. So that's kind of how that works. So now that we've seen kind of how it works from an authoring point of view, how you create these contracts, now let's see how it works from a kind of user perspective. So that's to say, if I want to interact with the smart contract, what do I do? Alright, so we have two options for this. One is a smart interface, the other is a manual interface. So in the current version of Marlowe, there's only actually 4 types of inputs. And you can tell this by there's these 4 empty arrays, right? And these 4 kinds of inputs are committing money, redeeming money. So by commit, I mean like a deposit into the system, redeeming money, claiming money, and then choosing a value, right? And so we'll kind of see how all these are used. But to kind of run through this contract that we have up here, and by the way, if you want to see examples, there's 3 examples given. One's like a crowdfunding smart contract. The other one's like a escrow smart contract, and the other one's a deposit incentive smart contract. Okay, and so the way the smart contract works is that person 1 deposits 100 ADA, person 2 deposits 20 ADA, and then we have these observations, like I mentioned before, and these observations could be, for example, some sort of oracle, or they can be some sort of user input. So if person 1 chooses something, basically does any action, then it allows both parties to redeem the ADA they inputted into the smart contract. However, if they don't do anything for 100 blocks, then we pay person 1 20 ADA, and then we allow them to redeem their money afterwards. And so the idea is you're paying somebody to deposit money into the system and keep it there for a certain amount of time, which is why it's called the deposit incentive example. So what are your potential actions, right? So because this program language is fairly restricted in what you can do, the system could automatically figure out the different kind of options that a player could do in any given step. So you can see right now we're at block 0, so at block 0 at the start of the execution. And you can see player 1 can make a commit of 100 ADA expiring on block 200. So if you add action, you can see we added to the input a cash commitment ID 1, and then we're saying we're depositing 100 ADA that will expire at block 200. You can see we can actually continue to put more actions, right? So this action automatically updated to show player 2 can now also make the action. And the reason why is because Marlowe allows you to do multiple actions within the same block, right? So you can see over here with our 2 commit cache boxes, there's nothing that says that these have to occur in different blocks, right? So it's possible that we get both commitments inside the same block. But for now, let's just say, okay, we're gonna put them in different blocks, and so the way we step to the next block is to press the execute button up here. So you press execute, and you can see now we're at block 1, and then the contract state has been updated. So now you can see we have some ADA input into the contract state, and then it is not redeemed. That is to say, nobody has taken money out of it yet, and that's your current contract state. So now at block 1, we can say, okay, the other person now commits their ADA to the system, and then we can execute that. Okay, and as you can see, as we execute statements, the contract updates, and this is what I was talking about earlier, right? And so whenever a box gets used, the contract is updated, and that box kind of gets removed. So you can see the contract we're left with here, if I just refresh, it's actually like the inside of what we had over here, right? So for example, let's redo it to just see it happens again. You can see here I have 2 commit cache blocks, right? And once I step to the next block that includes my first commit cache, the first one disappears, right? And there's only the second one left because we've exhausted this option as an input, right? And so if you're wondering how the Marlowe system works in kind of more detail, is that whenever you start a new block, it processes all the inputs until it gets to essentially no op. That's to say, there's no, like, any input you could possibly process will cause no change in the state of the contract, right? So as more happens in the contract, you're always making progress towards null, towards an empty contract. So you'll see at the end of this demo, we'll end up with a contract that only contains null. That's to say, it'll only contain nothing. So let's kind of keep going. So we're going to add the action to recommit for the player 2, execute that, and then now because this condition depends on either adding an action for player 1 or waiting for 100 blocks, let's just skip forward in history. So we're going to go from block 2 all the way to block 100, and then we're going to execute that. And now we skip forward to block 100, so now the condition is removed, right? Because one of the branches got fulfilled, and the only option that's left is being able to pay player 1 for depositing his input for 100 blocks, right? One thing to note is that the contract state is actually only 2 things, right? So you can see that there's only 2 arrays in here. The first array is a set of cache commitments, and the second array is a list of choices. Right, so early in this contract, I was showing you guys the player can make a choice, and those choices would be saved in history, represented by the second array over here. So now that we've gone over here, player 1 can claim their payment of 20 ADA, and then now we've done this, and we can execute it for good measure. We now have the block called both, which has like a both contracts will run. So the way you can think of Marlowe as is a way to compose these kind of very simple contracts. So you can say both takes 2 contracts as an input. One of it is a contract that is just redeem, and the other one is a contract that is just a redeem. Okay, so let's redeem ADA for player 1 and redeem ADA for player 2 and execute it, and now we're down to the null contract. It means there's nothing that can be done anymore. And we can see the output of running our entire contract over these 103 blocks is we redeemed a certain amount of money for both players, essentially. And so that's kind of the execution of Marlowe. And if you want to go through some of these other examples, again, you can go to the YouTube description and kind of try some of them out for yourself. Remember that if you cause updates, like if you want to update your contract on the left hand side to change some boxes around to play it with it yourself, you can use this blocky to code to blocky to kind of sync the left and right view. So I mean, if after watching this video you decide to go author something, feel free to share it in the description of this video. I'd love to check out what some of you make. The set of what you can do so far is fairly restricted. as this is kind of like the first version of this tool, I guess. There's a few different possibilities for things you could author. So now let's go back to what we had before and kind of have a deeper look into how it works. So the code itself, as I show you, renders down to this like set of instructions, which is a domain-specific language inside Haskell for this specific case. And so that's why we get these numbers that are stripped down, like all the titles or variable names are removed, and then we're just left with numbers. And these represent Haskell definitions provided in semantics.hs, which is in a GitHub repo owned by IOHK. So again, the link to this will be in the video description. So if you want to check out the code from Marlowe, I'll have a link to this and you can kind of check out how it works for yourself. But this file is not that big, so we'll go over kind of the different steps that can happen. It should only take a few minutes. And then you'll have a much better understanding of kind of how Marlowe works from the Haskell's perspective. So we start off with a few definitions. Just the key is an integer, person is a key, random and block number are just integers. And then we have a concept of observable things. And in this case, because it's a fairly small system, we only have random and block number as kinds of observable behavior. But you can imagine in the future, as we develop Marlowe more, there could be different kinds of ways you could kind of observe various things that come from the outside, right? One thing I didn't show you, I guess, is that if you go back to these contracts, I mean, there's quite a few boxes here for the observers, so you can kind of compose them together with the or observer and observer, this kind of stuff. So there's some boxes I haven't shown you, but you can see kind of here, this is those three menus are kind of the only boxes, so there aren't that many of them. So next we have the OS, which is kind of like the environment. So we're pulling data that is available to us from the blockchain, such as the block number, and then we start off with block 0. Okay, and then cache, again, is just an integer. We have a timeout, and timeouts are not in time. Timeouts are measured in blocks. So as you may have noticed in the contract I was showing you earlier, there's actually a timeout. For example, it said like if player 1 deposits money, but player 2 never shows up, and by never shows up, I mean does not show up within 200 blocks, we consider this a timeout. And then we allow player 1 to withdraw their money, saying player 2 never showed up, okay, you can just take your money out, and then no financial loss for you. So we have these IDs just to make sure that things are unique. So there's nothing special about these IDs, and in fact, they could be removed later on, I guess, and I think this is one of the work items that they have to have these IDs automatically generated instead of having to specify them yourself. We have commit cache, which is just an ID representing the commit cache. So like your first commit cache would be ID 1, your second commit cache would be ID number 2. You have the person who commits the cache, number of cache they committed, and then the timeout, right? And so if you're not familiar with Haskell, hopefully this is still readable. It should not be that complicated, I guess. But if you have any questions about how Haskell works for this specific case, feel free to ask a question in the YouTube comment section. I'm sure myself or somebody else could answer any questions you may have. So now we have cache redemptions, which is again just the ID to a cache commitment. Because remember, you redeem kind of a cache that was committed, and then the person, and then the amount of cache they've redeemed. So now what do we have for inputs to the system? Remember I was telling you guys earlier, there's actually 4 kinds of inputs. One of them is the set of cache commitments. The other one is a set of redemptions, right? So it's just a thing up here. And then we have a map of choices, and then a map of payment requests. So these are 4 kind of inputs you can have, and you can play around with these 4 different kinds of inputs in the examples that were given in the Marlowe website. So when we have a contract, there's actually a few different things a contract can be, which is defined by these actions here, right? And then whenever you have a contract, it's actually just a set, sorry. This is slightly different. But so these actions are, I was confusing with the next section. These actions are just for like logging purposes. So you can see you have like a successful pay, expired pay, failed pay, and so you can kind of use these logs to debug your smart contract, see kind of what's going on in execution, this kind of stuff. Right, so for example, if you're writing a smart contract in Marlowe, you could say, for example, we never want something to happen in this specific situation, and you can use formal verification to make sure you never encounter this specific action in a specific situation. So that's kind of what this is for. And then I'll show you guys how these actions are concatenated later on as we take steps within the Marlowe system. Yeah, so this is what I was originally thinking of, the state. So there's only 2 things that are added to your state. As I showed you guys earlier, the first one is the actual cash commitments, which is just the ID to the commitment along with its status, right? And the status, which is not here, is either it's not redeemed or it's manually redeemed, right? And when it's not redeemed, remember you have to keep track of the timeout because it may end up timing out. And then the SCH is just the concrete choices. That's the player choice. Remember we had a way for participants in the smart contract to make a choice. And this may be useful, for example, in escrow smart contract where you want kind of like 2 out of 3 people to agree a certain thing happened. And so I would vote for something happened, and then Alice would vote for a certain thing happened. There were 2 out of 3 voting for example, concrete choice number 1, and so that's what would prevail. And so that's kind of what these concrete choices are supposed to allow. As I showed you guys earlier, we have a few different boxes for money. We had in the example I showed you guys earlier, the constant money, which is just like, for example, deposit 100 ADA, but you have, a few different examples, or not examples, but a few different options you can pick up from, but I think they're all like fairly straightforward. So these observations are the ones I showed you guys earlier to chain stuff together, such as player made a choice or some observation possibly from outside the blockchain has become true. And then I think the parts, the 2 parts that are kind of more important, and I think everything I showed you guys so far in the code is kind of leading up to this, is one, what is a contract? And the contract is the boxes, the red boxes I showed you guys earlier, and this is what the system can actually encode, right? So first of all is the null contract, and that's kind of what I was showing you guys as the last step, right? You would like to show that your contract always makes progress towards the null contract and eventually reaches it, right? Because then you know you have a fixed execution time and you'll eventually have completed the contract. You can have a commit cash box, a redeem cash box, a pay box to pay for one person the other, and then these 3 down here are kind of like these meta boxes, right? What does this say? They are used to chain contracts together, right? So the first one is both, and that's what I was showing you guys earlier. We said, for example, like you run 2 contracts at the same time, right? You allow person 1 to redeem their ADA, while also allowing at the same time person 2 to redeem their ADA. So those are like 2 contracts running at the same time. We allow a choice, and when we say choice, we actually mean to do kind of an if statement based on the condition of some observation, right? So an example of this would be like if you've observed that the block number has gone to a certain number, or if you observe that player has made a certain choice, then you can move to contract 1. But if the observation is false, you can move to contract 2. Right? So this allows you to do an if condition, and it also allows you to kind of have these external inputs that make a choice for you inside the system. We also have the when box, and this is like a time-based system, which is why it has the timeout. And so you can say like when this happens within a certain amount of time, do contract 1, and then otherwise if we time out, skip to contract 2. And so these are kind of the red boxes I was showing you guys earlier. Now what actually happens when we take a step, right? So what is a step? A step is a execution within a block, right? So remember that one block can contain multiple steps. The name for this is a small step system, where our system actually encodes every transition as a single element, if you will. And so this step function is defined for all the contract boxes that we define up here. Right, so for example, if you have a step over a pay contract, right, what do? Okay, well, if the contract is expired, then we log the action that the pay has expired, right? If we have right claim, and what is right claim? Well, right claim just means that you are the person that has the correct ID to make this claim. Then as long as your claim is smaller than the amount of money that you can withdraw from the contract, then you've successfully gotten the payment. Okay. Otherwise, the payment will fail. For example, there's not enough money in the contract. You cannot have a payment. You cannot make a payment to player 2 of this much money because there's just not enough money in the contract for you to do this. And that's kind of what the pay function looks like. For both, this, as I showed you guys earlier, fairly straightforward. You take a step in contract 1, take a step in contract 2, and then the result is both again. So as long as none of the contracts ended, your result is another both, where now you've also concatenated the actions. And you should note that this is actually not commutative in a sense, right? Because the way the actions are ordered will change. So if you care about the order of the actions, you have to kind of take that into account. If you have a choice, then it's like I mentioned, based on some observation. If it's true, you take the first contract. If it's false, you take the false contract. Okay. The when, similarly, just adds an expiration, right? So if you've expired, then you move to contract 2. Otherwise, you look at the observation, and based on the observation, you go to contract 1. And then if the observation is false, if the observation is false, then you continue like waiting. Right, so you say, okay, the observation is not true yet, so we have to just wait. So the way you think of it is that, block 3 would check, is this true? If not, okay, wait. At block 4, check, is it true? If not, wait. And so that's kind of what this represents. Whenever you commit cash, you would check if the commitment has expired, and if so, handle that. Otherwise, if in the set of commitments, so in this case, like, it's called commits, but this is actually kind of, in my opinion, not a really good name. This commits up here is actually inputs. So when we say CC inputs, we say get the cash commitments inside the inputs, and then if you are a member of the cash commitments for the inputs, then you've successfully committed, right? And then whenever you make a step on the commit cash block, you also fill in the map for the choices, I believe, or sorry, not the choices, the commits that have been made in the state, right? So this is why we have like a map insert over here to say you've made cash commitments, and it's either like manually redeemed or not redeemed yet, and there's a timeout until this happens. So that's the commit cash block, and then lastly we have the redeem cash, redeem commit cash, and that one is just we look up the identity if there's just a person. That's to say, if there exists such a redemption option for this commitment, then we check are you the person for this commitment. If so, then you redeem it. Otherwise, nothing happens. And then if you've redeemed this already and you try and redeem it a second time, then we log the action duplicate redeem, right? So in your log for your smart contract, you would note that you've accidentally redeemed 2 times. And then in the case that there is no such commitment, then you just go to the other branch, which is nothing, and just nothing happens. And so these are all the steps. One thing I should note is step block. So the function I just showed you is step, right? And so whenever you step over a block, you actually call these steps multiple times until nothing changes, right? The state no longer gets updated, right? So remember, every block, these steps get called multiple times. And also, whenever you call the step block, any cash commitments that have been made and expired are now available to be redeemed by the person, right? So if I committed, for example, in a previous contract 100 ADA and that expired, this will handle like unlocking your funds and allowing you to redeem it again. And so one thing you might be wondering is, okay, in our example previously, we show you that we got to the step where the user had to make an actual input to say, okay, I'm redeeming my money to get it back to me, right? And we're wondering, why do we not just send a transaction to just send the money back to the person, right? And the question is like, who will pay for this transaction, right? Because whenever you make a transaction on the blockchain, someone's got to pay for the transaction fee and all this kind of stuff. And so to kind of avoid this kind of problem, it operates on a pull system. That's to say, whenever your funds get released, you have to manually pull it down from the contract. It will not be sent to you automatically. And so that's kind of the reason why we had this redemption box in the first place. So that's kind of how that works. Hopefully you enjoyed the presentation of how the first version of Marlowe works. As I mentioned earlier, as the research progresses and the code gets built, this will eventually probably run its own testnet, running on Cardano, and so it's something to look forward to if you're interested in these kind of simple financial contracts on a blockchain that's meant to be easy to verify and also CEO friendly, where you don't need to code to be able to get it all working. And with that, hope to see you guys in my next video. Take care.